Welcome, welcome, welcome. This is chapter 9. We're starting chapter 9 today. And, you got to let me know if we need to do more in chapter 8. We're not going to have a test in chapter 8. So all your worksheets, your quizzes are the test. So, we'll just keep doing this. We'll do a bunch of worksheets. You'll turn them in. I'll see if you seem to be understanding the material. And if we need more practice, we can go back and do that. But you got to let me know. And then, of course, I'm kind of getting a feel by looking at your work, and it's looking pretty good right now. But, some people really have it. Some people are a little bit confused. If you're a little confused, go watch the videos over again and do the worksheets over again. Okay. And of course, talk to me if you have questions. Email me, text me. We've got a video chat tomorrow at 11, or 11:30. So you can also do that. And if you want to do a video chat anytime, let me know and we can. I can chat anytime and do some example problems if you need to. But you gotta be responsible for teaching yourself this stuff. So here's chapter 9. It's a little bit different, a lot different than chapter 8. Chapter 8 we had 2 samples, and in chapter 9 it looks like we've got 2 samples, but they're really 2 different variables. So instead of, okay, we've got 2 samples like in chapter 8, chapter 9, we've got a variable, an X variable, and a Y variable. And we want to see if the 2 variables are related to each other. So as in here, you can see as the X variable gets bigger, the Y variable gets smaller. So that's what we're looking for in chapter 9. Is there a relationship between the 2 variables? We call it a correlation. Okay, so that's what we're looking at in chapter 9. And it's going to be 3 parts to it. So first off, we're going to see if there is a relationship between the variables, if they're correlated. Then we're going to find out what that relationship is. And that's called the regression equation, or the linear regression equation. That's going to be the relationship between X and Y. And then lastly, once we know the relationship, we'll find a prediction interval for a particular X value. So in chapter 9, we're going to be graphing the X and the Y, and then we're going to actually be going to find the relationship, the equation that describes the relationship between X and Y. And that's the regression equation. So some of you did this in pre-calculus. We're going to do it, again in statistics. You will have to graph it. So if you don't remember how to graph, you're going to have to ask me questions or go back and, teach yourself how to graph. But we're going to be coming up with a line. The regression equation is going to be y equals mx plus b. So it's going to be the line, equation of a line, y equals mx plus b. So, and I can go over that if you have questions, and I will go over it as we do the problem, but you may, have additional questions that you want to ask me, or stop the video and go back and watch it, in slow motion. Okay, now, so we're doing practice worksheet E, and it's on the Classroom if you want to look at it. And what we have is we have data in some old growth forest quadrants. What these wildlife researchers have done is they've gone out and they've seen how many horned owls are in a quadrant and how many spotted owls. And we're concerned about spotted owls because they're endangered, and we're afraid that they're being, they're going to go extinct. So one hypothesis is that the horned owls are out competing the spotted owls, and that's one of the reasons that spotted owls are not as prevalent, because the horned owls are more efficient. So we're seeing if there is a relationship between the horned owls and the spotted owls. So we go out the quadrant, the wildlife biologists go out there and they see how many are in a quadrant. So in this particular quadrant, there were no horned owls and 4 spotted owls. So what we're going to do is we're going to plot this data on our graph. So the horned owls is the X coordinate, the spotted owls is the Y coordinate. This is the X, this is the Y. So this point right here, there were no horned owls and 4 spotted owls. That's going to be right up here. So that point right there. And we're going to have dots all over this graph. So I usually use triangles to indicate the original data. So that right there is that first quadrant where there's no horned owls and there's 4 spotted owls. The next quadrant, there was 1 horned owl and 4 spotted owls. So that's going to be right up here. So I'm going to put another triangle there. This quadrant, there were 2 of each. So 2 horned owls, 2 spotted owls. That's that point right there. Here, this quadrant, there were 3 horned owls and 2 spotted owls. So that's this point right here. And here in this quadrant, there were 4 and 2. So that's here. And then lastly, there were 4 and 0. In this quadrant here, there were 4 horned owls and no spotted owls. And of course, I just made this data up. This isn't real data. And I made it up, and I'll make up all the data in this chapter so that the equations are going to work out really nicely. And you'll see what I mean by that. So the equations are going to come out to be pretty even. And the reason for that is that way you can graph it accurately and I can grade it accurately. So it's always going to come out. The equation is always going to come out to be a nice decimal, a good decimal. So if you get a weird decimal, you know you've made a mistake. Okay. So you can see that it looks like there might be a relationship here between the horned owls and the spotted owls. Well, we have to prove that statistically. So that's what we're going to do in step 1 is we're going to see, is there a relationship? Are the data correlated? Okay. All right. So step 1, we still follow the same 4 steps that we always do in hypothesis tests. So our hypothesis is going to be there is a linear relationship between the number of horned owls and the number of spotted owls in a quadrant. And a linear relationship, of course, means we're going to be able to find a straight line that fits that data. And that's what we're going to do. So step 1, what's the hypothesis? Well, the hypothesis is we're going to have a null and an alternate, like always. And the same 4 rules still apply, same 4 steps. It's a new variable, however, okay? So instead of a mu or a p, mu for average, p for percent, we're going to have another Greek letter called rho. And rho looks like an upside down 6. So it looks like this. Okay. And rho is a Greek letter for R, which has come to be used as the name for the correlation coefficient. Okay. So, and what that means, what the correlation coefficient means, is it tells us how close to a straight line the data lies. So if all my data is perfectly on a straight line, I draw a straight line, it could be any kind of a line, straight line, and all the data falls perfectly on that straight line, then we say that the X and the Y are perfectly correlated, and the correlation coefficient R, so this is a correlation coefficient, would equal 1. And if the slope is positive, if the slope is going up like this, then it's equal to positive 1. If, on the other hand, the line is going downwards, and all our data is like this, then R is equal to -1. This is a negative correlation. This is a positive correlation. So R, of course, means it's a sample. And if I put a rho in there, that would be the population, right? So nobody knows what rho is. Only God knows what rho is. But R, we can actually take a sample and figure out. So we're going to find an R for this data. We're going to come up with a correlation coefficient for this data here. And then our hypothesis is going to be, well, the data is correlated or it's not correlated, right? So not correlated is going to be if you have a graph like this and the data is all over the place. I mean, you look at that data and you'd say, oh, that doesn't seem like there's any kind of a correlation there, right? This is just scattered all over. There doesn't seem to be a relationship between the x-axis and the y-axis. So in this case, the correlation coefficient is going to be close to 0. Maybe it would be like positive 0.08 or something like that. Okay. So if the correlation coefficient is close to positive 1 or close to -1, that means the data is correlated. So if the data is kind of scattered around like this, around the line like that, the correlation coefficient might be like 0.9. If the data is all over the place like this, the correlation coefficient is going to be closer to 0. So closer to 0 means it's not correlated. Closer to +1 or -1 means it is correlated. So you got to remember that. It's weird. Write it on your formula sheet. I did include a formula sheet, by the way, in Classroom, so you can download that. So we're on to our next formula sheet. It's chapter 9, 10, and 11 formula sheet. So on that formula sheet, we're going to start here at the top. So the top half is chapter 9, and then we get into chapter 10, and chapter 11 is all the way at the bottom. So we're going through chapter 9, linear regression right now. So correlation coefficient close to 0, not correlated. Write that on your formula sheet. Correlation coefficient close to +1 or -1, that means they are correlated. Okay, X and Y are correlated. So our hypotheses are going to be rho equals 0. So the null, rule number 1, the null has to have a 0 in it. And number 2, the alternate hypothesis is going to be rho does not equal 0. So anytime the correlation coefficient is not 0, then there is a correlation. The only time it's equal, there's no correlation, is if the population correlation coefficient equals 0. The sample correlation coefficient, R, may equal any number. We've got to get it pretty close to +1 or -1 to say that there is a correlation. Okay? So this is going to be, so write these down as your hypotheses. Put those right on your formula sheet so you don't forget those. And of course, you've got to write it exactly like that. If you write it any other way, you're losing points. So this means, this is weird, our conclusion is going to be about the alternate hypothesis. The alternate hypothesis is rho doesn't equal 0. That means that they are correlated. So not equal to 0 means that they are correlated. Just because there's a not in here, do not put a not in your conclusion. So I can or cannot be, and in this case, we're going to do it at 95%. So I can or cannot be 95% confident that number of horned and spotted owls are correlated. Okay? So not equal to 0 means that they are correlated. So that's a common mistake. Again, write that on your formula sheet. Write that right on there so you don't forget that. That's easy to forget. That's a little bit confusing about this chapter. Not equal to 0 means that they are correlated. Okay? It'll always be like that. It's always going to be the same conclusion, that the X variable and the Y variable are correlated. That's always going to be our conclusion. Okay? You do have to write out here what is the X variable and what is the Y variable. So just don't say X and Y are correlated. Tell me what X is and what Y is. Again, so your mom understands what you're talking about. Okay, how do we do that? Well, it's a two-step process. Well, first off, let's jump to step 2 here. And this is a little bit different. It's always going to be a t distribution. And because it's not equal, it's going to be a two-tailed t distribution. So we're doing 95% in the middle. So it's going to be 0.025 in each tail. And here's the weird thing. Here's the new thing that's weird is the degrees of freedom is different. The degrees of freedom is equal to n minus 2, where n is the number of data points, the number of dots on your graph. Okay, so I've got 1, 2, 3, 4, 5, 6. So degrees of freedom here is going to be 6 minus 2. And it's 2 because there's two dimensions here, two variables. There's an X and a Y. So instead of, n minus 1, it's n minus 2. It's on your formula sheet, so circle that so you don't forget it. So degrees of freedom here is going to be 4 with 0.025 in the tail. So I look on my T table. 4 degrees of freedom, 0.025 is 2.776. And of course, it's plus and minus. Okay, so it's plus and minus 2.776. So the critical value, plus and minus 2.776. This chapter, every single problem in this chapter, the critical value will be plus and minus. All right. Now, to get our t's, this is step 3, and this is the biggest step. It's a little bit involved. To get our t, we have to do 2 steps. We have to do 2 steps. And these are the 2 equations at the top of your formula sheet. So the very first equation's up there at the top of your formula sheet. And you can see it's a pretty complicated equation. It's a crazy equation, okay? It's probably the most complicated equation, one equation we do. That the correlation coefficient is equal to the sum of the xy's minus the sum of the x's times the sum of the y's all over the square root, and it's this big crazy square root. On the bottom is n times the sum of the x squareds minus the sum of the x quantity squared. I got to check it to make sure I'm remembering it right. Times, this is times, another parentheses, n times the sum of the y squareds minus the sum of the y's quantity squared. You multiply those 2 numbers together, you take the square root of the whole thing. So there's really 3 numbers here in this equation. So I kind of think of it like this. R is equal to this number on the top, and then the 2 numbers on the bottom, and you take the square root of those 2 numbers on the bottom. You multiply the 2 numbers together on the bottom, and then you take the square root of those. And I want you to write out those 3 numbers for me. You know, we're going to calculate those 3 numbers. You're going to write them out for me. And the reason for that is you're going to use them later on. So those numbers you're going to use in step 1, the hypothesis test, but you're also going to use it in step 2 when you do regression. So you want to keep track of those 3 numbers right there. The numerator of the correlation coefficient and the 2 numbers multiplied together in the denominator of the correlation coefficient. And then, of course, you are going to take the square root of those numbers on the bottom. Okay, so how do we get those numbers? And this is confusing, so make sure you go slowly here, take good notes on it. The rule is everything that has a summation in front of it, we need a column of that, okay? So we have an X column, we have a Y column. Right here I have sigma XY. That means I need an XY column. So right between the X and the Y column, I usually put my XY column because it's X times Y, and I can just multiply those 2 things together and put the answer right there. So the sum of the XY column means multiply X times Y. So you multiply every one of these. 0 times 4 is 0. 1 times 4 is 4. 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. And 4 times 0 is 0. Be careful when you multiply by 0. Remember, it's 0. How do I get the sum of the XY's? I add up that column. So 4 and 4 is 8. And 8 is 16. And 6 is 22. So the sum of that column is 22. That's what's going to go right in there. So this is going to be 22. Okay. So my R equation, now let me see here how I want to do this. Maybe I can do it down here. I'll just do it right here. R is going to equal 22. And I think I forgot something there, didn't I? I did forget something there. There's an N in front of this. Okay, so it's N times the sum of the XY's. So N, remember, is 6. So it's 6 times 22. And then we have the sum of the X's. Well, let's just add up the X column. So that's this column right here. This is the sum of the X's. So that's 3, and 3 is 6. There's 10. Looks like the sum of the X's is 14. And then the sum of the Y's. I add up the Y column. This is 8, 10, 12, 14. So the sum of the Y's is 14 also. So my numerator is going to be n times the sum of the xy's minus the sum of the x's times the sum of the y's. And of course, you can do that all in one step on your calculator. That's the number that's going to go in right there. Let me do that while I'm thinking about it. That's going to be 6 times 22 minus 14 times 14. That is negative 64. So that goes right there. You're going to need that number later. So write it down because you're going to use it again. Okay, so that's the top of the correlation coefficient. The bottom is going to be this. It's going to be 6 times the sum of the x squareds. Well, the sum of the x squareds means we need an x squared column. So right here, I'm going to put an x squared column. Right next to the x column, put an x squared column. You're going to have 5 columns by the time we get done. To get the x squared column, I just multiply, I square this column right here. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 4 squared is 16. And then I add that column up. 16 and 16 is 32, and 9 and 1 is 10, so that's 42, and 4 is 46. So that's the sum of the x squareds. So right here, this is going to be 6 times the sum of the x squareds. Right there is the sum of the x squareds. Now it's minus the sum of the x's squared. The sum of the x's is 14. So I square that. So be careful. This is the sum of the x squareds. I square the x's and then I add them up. This column here, I add up the x's and then I square them. And they're different numbers. So make sure you keep that straight. That's confusing. The next, now we do the same thing for the y's. So I have 6 times the sum of the y squareds. So over here, I've got a y squared column. 4 squared is 16, 16, 2 squared is 4, 2 squared is 4, 2 squared is 4, 0 squared is 0. So there's 16 and 16 is 32, and there's 3 fours, that's 12. So 32 and 12 is 44. That's the sum of the y squareds. So this is 6 times 44 minus the sum of the y's quantity squared, so that's 14 squared. Okay? So that whole thing, this is pretty complicated. The most complicated thing we've done so far probably is going to be our correlation coefficient. So let's calculate what's the bottom number here. 6 times 46 minus 14 squared. Your calculator will do PEMDAS correctly every single time. You will make lots of mistakes, but your calculator will do that, correctly every time. And that is 80. That's the first number inside the square root here on the bottom. The second number, 6 times 44 minus 14 squared, all I have to do is change that 46 to a 44, is 68. And all this is going to do is it's going to tell us the correlation coefficient. This is not our T. This is just the first equation at the top of your Chapter 9 formula sheet. So when I do this, let me do this here. I have negative 64 on top divided by square root, and then I'm going to do parentheses 80 times 68, and then close the parentheses. Don't put a parentheses on the 2 parentheses on the bottom. Use a times, not a parentheses. Otherwise, it'll take just the square root of the first number, and then it'll multiply it by the second. So don't use 2 parentheses like this on the bottom. Do it like this. So when you're doing this in your calculator, do it like this. 80, and then do times 68. Otherwise it'll just take the square root of the 80 and it won't take the square root of the 68. But you have to multiply these two together. So put them inside of parentheses with a times between them, not a parentheses. And then multiply, then take the square root. So let's see, what do I have? I have square root of that. And I'm going to put that in memory. And that turns out to be negative 0.868. So this turns out to be R equals negative 0.868. Okay. This is the sample correlation coefficient. So it looks like it's, there's somewhat of a correlation there. Negative 0.868 looks like it's, it's pretty close to 0.9. And negative 1 would be a perfect correlation. So negative 0.9 is pretty close to a good correlation. But we haven't proven, that doesn't mean we say we can be sure that they're correlated. We've got to actually prove that. So the way we do this is with another equation. And this is tricky because the second equation looks simpler, but it's actually where most people make the mistake. Okay, so the second equation, so make sure you save these three numbers here, negative 64, 80, 68. You're going to use those again. So, do not get rid of that equation. Okay, here's the equation for our t. And this is the second equation at the top of your formula sheet. T is equal to, and this is our t, so this is step 3, is equal to r divided by the square root of 1 minus r squared over n minus 2. The denominator there is just the degrees of freedom, so we already know. So this equation is negative 0.868 over the square root of 1 minus negative 0.868 squared divided by degrees of freedom is 4. Okay, so this equation doesn't look nearly as crazy as that other equation we did, but 90% of the people that get this wrong get it wrong because of this equation. They get the correlation coefficient correct, and then they screw up this equation. The reason they screw it up is because this negative here, if you square that negative on your calculator, so if you type it into your calculator just like this, you'll get it right every single time. But a lot of people will type it in something like this. They'll type it in without that parentheses. So if you type it in without that parentheses, you'll get it wrong. So 90% of the mistakes here come in this little problem right here because people do not put these parentheses in here. So here's what, and one of my students, eventually clued me into this and gave me this idea. They said, Heil, you should actually have them write it out and do it this way every time, and they'll never make a mistake. So let me tell you how to get this. Write this on your formula sheet, and you'll never get it wrong. So this is our t. If you do it like this, our t is going to equal answer. So right now I have negative 0.868 in my calculator, right? I also have an answer key on my calculator. So I'm going to use that answer key to repeat that number. And if I do that, I will never get it wrong. So if you type it exactly like this, you've got to know where your answer key is. So on the Casio, it's a button all by itself. If you've got a Texas Instruments, you have to hit second, and then, I don't know, it's like the number 0 or something down at the bottom, second, and then answer key. But if you do it like this, if you do answer divided by, and then you're going to do, let me think if I can remember this, square root, and then you have to do 2 parentheses, 2 left parentheses, then you're going to go 1 minus answer squared close parentheses, divided by, and then the degrees of freedom you can just usually remember. It's just going to be 4, 6, or 5, or 3, or something like that. So then you just go divided by degrees of freedom, close parentheses again, and then hit equals. And if you do that, if you do it exactly like I've written it out here, answer divided by square root, 2 left parentheses, 1 minus answer squared, put this squared inside, make sure that squared is inside this other parentheses. You've got to do it exactly like this, divided by degrees of freedom, close parentheses equals, and you'll get it right every time. So let me see if I can do that. Answer divided by square root, 2 left parentheses, 1 minus answer squared, close parentheses, divided by degrees of freedom is 4, close parentheses, and then equals. And that gets me my t, our data's t, which is negative 3.49. So this equals negative 3.49. These answers are at the bottom of the of your worksheet, by the way. So there should be a negative 3.49 down there. So our data's t is negative 3.49. And of course, negative 3.49 goes over here. It's smaller than negative 2.776. So this is in the can region. And we can be 95% confident that horned owls and spotted owls, the number of each of those in the quadrants are correlated. Okay, so that's part one. And that, how long did that take? That took about 30 minutes. Holy cow. So that's just step one of this. And I think what I'll do now is I'll end the video, and then we'll come back and do parts 2 and parts 3 on a separate video. So there'll be another video finishing this worksheet, finishing this same worksheet.